Okay, so topic 3. Before I talk about this topic here, let's do a quick recap of 1 and 2. Basically, for this entire unit, I've kind of said I have 3 main outcomes we need to cover for each section. First outcome, we got to talk about the nitty-gritty details about each type of function, some of the unique properties, things like with square roots, you can't square root a negative number. Right? Today, when we talk about rational functions, it also has unique properties only to itself. On a rational thing, a fraction, you cannot let the bottom of a fraction be equal to 0. Right? So look at the example I have on the board there. What is the one value x cannot be? Nope. Negative 2. Yeah. If x was negative 2, we have a problem. Right? And we've kind of discussed this already a little bit. I've been hinting at this in our first section. If things divide evenly, then it can create maybe a hole in the graph. This one I don't think creates a hole in the graph. This will have what's called an asymptote. If you guys remember that term from last year, we'll review it again in my notes in a little while here. But that would be like a unique property of a rational. So that's topic 1. What are some of the unique properties? Topic 2, I need you to know what the graphs look like, including how to move them around. And so, we already know the basic shape of a square root graph. The basic shape is that little like half parabola, right? But it is possible to get all sorts of other weird shapes, right? I just showed you 4, right? The first one was a half parabola. The second one looked almost like a V, I believe it was. The third one looked like a quadratic again. And the fourth one, there wasn't even a graph for, right? So there are all of these unique sort of one-off circumstances you should be prepared to be able to comprehend. So I got to talk about what some of the basic graphs look like for rationals. And then the last one, you have to be able to solve algebraically. So, sound good so far? Okay, let's get to it. If you guys feel like we want to start blurring into part 2, we can try, by the way. I'll leave it up to you guys when we're done. So first example here, we'll make it fairly straightforward. If I give you f of x and g of x, Peter, can you grab the door, please? And we want to write them in this notation here. What does this notation mean? F divided by g, close bracket x. What does that mean to you guys? Yeah, it literally means take the two fractions and divide them, right? So based on that, if I were to give you x squared plus 6x plus 9, and I ask you to divide it by x plus 3, honestly, we've done this kind of already, haven't we? Like, this is something that we did in Unit 1. Except in Unit 1, I made you the promise that they should always actually divide by each other. If they don't actually divide, then we're not going to work with them. So you can probably imagine the first one I give you should actually divide, because you can factor that top, right? It gives you x plus 3 with a second x plus 3. And then the bottom is x plus 3. So will these actually divide? Yeah. What are you left with? You're left with the equation x plus 3. So what would this graph look like? Well, it would look linear. I would expect it more or less to look like a regular old-fashioned linear graph, like this. But what's the domain? Can you have every value for x? Or is there a value for x you can't use? You can't use negative 3, right? Even though in our new function right here, our final composite function, even though for f over g of x right here, even though that now looks linear, way back here in this step and this step here, you couldn't use negative 3. So the notation I started showing you is that you would then have a hole in the graph over here at negative 3, which we'd use like an open circle for. You guys recall talking about this a bit? It really wasn't the point of Unit 1, but it's very much the point of Unit 2. So what's your domain? Well, it's not x is an element of the real numbers. Your domain would look, sorry, I should say more room on the slide. Your domain would look better like this. You'd go from negative infinity up until negative 3, but you can't include negative 3, right? So I would use a curl bracket around the negative 3, implying that that's the one number you can't use, right? Well, then you pick it up back again on the other side of negative 3. So we actually restart by using negative 3 again, and we go till positive infinity. It's a little cumbersome, because really what this notation means is go from negative infinity all the way up till negative 3, but you can't have 3. You could have 2.999 repeating. You could have 3.00001. Just the one number you can't have is 3, right? Or negative 3. Right? then pick it back up again on the other side and go to positive infinity. What about your range? What sort of y numbers can we have? Well, I mean, as I look at this graph right here, it sure looks like I can have them all, like it goes from top to bottom. But if there's a hole in the graph for the x value, doesn't that mean that there should be a hole in the graph for the y value? Do you guys remember how to find that hole? Right here you have an equation. Right here you had an equation. Right here you had an equation. Now in equation 1 and in equation 2, you couldn't plug in -3. For you guys doing limits, this is kind of what we've been talking about, right? You cannot plug in -3 for x right here because it causes you a problem. You can't plug in -3 for x right here because it causes you a problem, but why couldn't you plug -3 in for x right here? There's no problem anymore. So if you plugged in -3 for x, if it was now allowed, -3 plus 3 would give you 0. I now know where the y value is. The hole in the graph would have been at -3 and 0. So to write the range, you could write it in the same notation. -infinity, comma 0, u, 0, comma positive infinity. Let me show you another notation. You could just say x, or no, you wouldn't say x. That's not range. I was just going to say my board has been working so good. And then it stopped. Ah, so good. Come on. Come on. You can do it. Or you can't, whatever. There we go. All right. Your range is going to be y. You could just say y is an element of the reals, and then you could just tell me the one exception. You could say y can't be 0. Did that other way of writing it? You guys have seen that before, right? The say what it is with the one exception. Both kind of mean the same thing. Sorry, that's such a mess. It's not the prettiest I've ever written. So. Okay, did that first example make some sort of sense, though, right? The idea that we are going to try to long divide them, or whatever, however you divide them. If they do divide evenly, it creates a single hole in the graph. This is what I want to start focusing on now. What if they don't divide evenly? If I were to give you x squared plus 5x plus 6, and I were to ask you to divide it by x plus 4. Right off the bat, what is the one value for x you can't have? -4. Okay, we're all in agreement on that, right? Now, it sure would be nice if I could like cancel away the issue. But when I try to factor this guy, hopefully you can kind of see. When you factor the 5x plus 6, it gives you a 2 and a 3. That doesn't have someone to cancel with. So this is now a rational function in which we don't have a hole in the graph. So I'd like to grab a graphing calculator now and kind of talk through some of the properties of this graph. So y equals. And the advice I'd give is bracket the whole numerator and bracket the whole denominator. Make sure you do them like, say, like this. X squared plus 5x plus 6, all in its own bracket, and then divide by a new bracket for x plus 4. Okay, depends on what brand of calculator or like what version of calculator you have. Does everybody have a graph on their screen that at least has this little flippy part right here and this little flippy part up here, but you may or may not have the straight line up or down? Okay. If you have an older version of a calculator, you probably have the line straight up and down, and you might be the only one. Does anybody else have that line that goes up and down? Okay. So that is on an older version of a calculator when they were drawing, continuity we were talking about in calculus. Basically, the calculator literally has to go like this, and then it's not allowed to like pick its pencil up and go back up to the top. So it literally draws a line all the way up and down. But this line right here, there is no actual graph right here, if you happen to see that one. So, do you guys remember what we call that like straight up and down line like that? Yeah, it's called an asymptote. Yeah. Essentially, if we were to graph this guy a little bit nicer, it would look something like this. It's at -4 is our issue, and it's basically dropping straight down like a rock. And then I mean eventually it's kind of turning around and going up there, and then over here it looks like it's kind of coming in, turning around, and then it's like dropping straight down like a rock again here. Like literally there is only one value you can't have, and that value is -4. If you wanted to try going to your table and you want to try typing in, like, say, -4, it would say, like, literally, it would say y equals blank. It literally can't do that, right? If you were to go to your table and ask x to be -3.99999, well, then it does give me a value. 3.9999 apparently is like 20,000. Way off my graph, but at least there's a value there. You guys get what I'm saying? So now we've talked about asymptotes before. Last year, you guys should have learned about the graph of 1 over x, which basically has an asymptote this way and that way. I'm drawing very nicely here. And it kind of does a little whoosh, whoosh shape to it. Did I make the sound effects last year too? Probably did. I always make the sound effects. Right? It has the whoosh, whoosh shape to it. Right? This graph has very similar properties. The one we just talked about, it does have a vertical asymptote. It has one vertically, but it actually doesn't have one horizontally. So we don't actually have to worry about one that way. But if I do want to ask you about the domain and range, that's going to be kind of tricky. So let's do domain here. Take a stab at it. How could you write the domain? Anybody? What's the way to write the domain? To -4. Curl brackets for both, because you can't use -4. And then union that with -4 to positive infinity. That'll work. Or if you don't want to write that out, you could write x as any number you want with the exception of -4. Like both of those would be valid ways of writing it. What about your range though? What's the lowest y value it can get down to? Looks like it just keeps going lower and lower, doesn't it? So your range would go from -infinity up until right about there. You guys remember how to find a maximum value on your calculator? I'm not going to bother finding it, but could I just label this as A right now? And you guys know that you could find that value. So it would go from -infinity up until that A value. However, would you include that A value or not? Like, should I use a round bracket or a square bracket here? You would, yeah, because you can include that A value there, right? And then you'd pick it up again somewhere over here at this minimum value. Why don't I call that one B just to save me some time? And then you'd start at B, include B, and go to positive infinity. See how we're starting to get some graphs now in the non-polynomial section where not every input or output is valid, and you get like these weird stretches where sure you can have everything from -infinity to -5, then from -5 to -1 you're stuck again, but then from -1 up you're good again. Right? So it really depends on the graph at this point. There's so many unique, weird ways that this could occur. So my goal over the next few slides is to give you a bunch of examples to talk through. So far, so good, though? Haven't lost you? Okay, so let's keep with my theme 1. Theme 1 was I need you to know all the different like unique properties of a graph. So that's what I've got on these slides here. When you divide two functions, if the remainder is 0, your rational simplifies to a polynomial. Is that terminology something you guys are familiar with? Your rational fraction, if it does divide, it turns back into a polynomial, and it'll have a hole in the graph, which we use an open circle for. I don't know that I used this terminology before. It's called a point of discontinuity. That's like its official math term, which kind of makes sense because this graph is no longer continuous because there's literally a gap in it. Right? We've talked about that in calculus too. See how this is actually better if we did it the other way, but sorry. Okay, anyways, that's the that's if they do divide. However, it's possible that the two functions do not divide evenly, right? So let's just factor these real quick. This would be x plus 5 with x minus 4. This is going to be x minus 6 with x plus 3. I'm not expecting this to look linear or quadratic with a hole in it. I'm expecting this to look crazy. How many asymptotes should you expect? 2. Where would the 2 asymptotes be? Yeah. I'd expect there to be 2 asymptotes where x is 6 and where x is -3. That's where I'd expect to see some asymptotes. So, I mean, this graph is going to look kind of messed up because there's going to be 2 sections of the graph where the graph just all of a sudden goes like and just falls right off a cliff, right? And it may even be one of those sorts of graphs. Maybe you've seen them before where it looks like it goes like I make good sound effects, right? Where you can hopefully see that you've got like 2 different asymptote sections there. Okay. The downside to rational graphs is that there really is no base rational graph. So you just need to plug it in your calculator and take a look at it. Okay. Anyways, let's skip over this one here. I got examples on the next few slides. Rational functions often look very different from each other. The shape really just depends on the 2 functions being divided. If you divide a linear by a cubic, it's different than a cubic by a quadratic. It's different than a factorable quadratic from a non-factorable cubic, right? Like, there's so many different permutations that I can't give you like a generic rule for this. So it just depends on what you're dividing. These guys right here, take a look at this one that you have right here. This one kind of cancels. Based on what I did here, we factored this guy, and then the x plus 3 canceled, but there's still something on the bottom. This graph then is going to have a hole where x is -3. There's going to be literally a gap in the graph, but then there's also still going to be an asymptote. You can tell me where the asymptote's going to be? You can't plug in -3 right here, right? Yeah, but 0 is still a problem, right? And 0 never canceled away. So this is a graph that has an asymptote and a hole in the graph. You could have one of each even. Those are the defining features of rationals typically. Typically, rationals are defined by either they did divide nicely and there's a gap in the graph, there's a hole, a point of discontinuity, or they don't divide evenly and you get an asymptote of some kind. But there's even more possibilities than that. So. Wait, let's try some graphs though. Okay. There is one base level graph I would expect you to know, and it's the one we did last year. It's your 1 over x graph. Okay. So this would be the only type of graph that I'd really expect you to be able to not need a calculator for. So the 1 over x graph, if you guys remember, it does the whoosh. It's like the slide going downhill, right? Do you guys recall this well enough from last year that I don't need to like go over the nitty-gritty details? That's your base level graph. Should I talk about it some more? Sure, mini review. Why does it look like this? Let's talk about the why. Do a quick table of values. What if x was, say, 5? Well, if x is 5, y becomes 1 over 5, which kind of explains why over here at 5, it's starting to get, I didn't draw it very nicely, obviously, but it's starting to get like shorter. What if x became 10? Well, then it becomes 1 over 10. Like as your x values get bigger, your y values become smaller. Does that logic make sense, Jimmy? Right, like I use like a seesaw kind of analogy. As your x's get bigger, like if x is 1,000,000, well then it's 1 over 1,000,000. Well, that's like really tiny. Right? Same thing happens here in the negatives. If x was -10, then y becomes -1/10, which is why it's on the negative side of the graph, but it's like super, super short in terms of height. Right? When x is in this region right here, or in this region right here, this is where x would be like a fraction. What happens when you divide a fraction by a fraction? Like what if you do 1 over a 10th? What is 1 over a 10th equal to? 10. Thank you. Do you guys remember doing this at all before? Like 1 over 10 is like 1 divided by 1/10. Or another way of doing it is like timesing by 10 over 1. Long story short, when you divide a number by like a fraction number, like a number less than 1, it actually makes it bigger, which is why all of these values right here, the x values are very small, right? They're all like, right here x is 1, here x is a half, here x is a 10th, here x is 0.00001, right? And what ends up happening there is when you reciprocal those and do 1 divided by that, it actually makes the numbers very large. So there's only one number you can't have, though. You can't have x being 0, which is why you have like that vertical asymptote running that way. Good question. So what I would have taught you last year was probably this. X is an element of the reals. And I would have said x can't be 0. I would have told you like the one exception. This year, I'd expect you to also be able to add to that something like this. Negative infinity up to 0, but don't include 0. And then start again on the other side of 0 and go to positive infinity. I need you to be familiar with either one. Depends on what they write us on the test. That make sense? For your range, literally range is the exact same thing. Because there's one value that you can't have right here, this graph will never touch the x-axis, so it also won't have a y value of 0. So if you really wanted to write out the exact same thing, your domain and range are literally the same for one of these graphs. Does that work for a mini review? Cool. Okay. So what I want to do here then is I want to practice manipulating this graph around. So what if I gave you x plus 3 to the minus 1? So a couple of things I want to kind of incrementally build with here. Do you guys remember that the negative 1 notation means 1 divided by x plus 3? Do you guys recall that rule? A negative exponent means 1 over top of. Well, hopefully you guys don't need a calculator to work on this then. What is the one value of x that you can't have? Okay, so I'm just going to draw on my asymptote real quick here at negative 3. Can't have negative 3. And then that actually kind of makes sense because doesn't x plus 3, doesn't adding 3 inside a function, doesn't that shift the graph this way to the left? Right. So, I mean, really that same sort of whoosh shape that I'm going to have here, it's going to be the exact same sort of shape that I had before. It's just all that I've done now is I've shifted the whole graph 3 units that way. So you probably don't really need a calculator to know what the rough shape of this graph looks like. Domain, everything but negative 3. Range, everything but 0. However you want to write that. X can't be negative 3, y can't be 0 is essentially the concept I want you to get there. Okay. Really, the two things I really wanted to focus on are, do you remember that the negative 1 notation means that it's on the bottom of the fraction? And then secondly, if I just do an x plus 3, doesn't a plus 3 shift a graph to the left? So we don't need to actually graph this thing. We should know what it looks like roughly. Okay, well, this one here, I wouldn't expect you to be able to graph this one just off the top of your head. Okay. I would, however, expect that you should be able to tell me the non-permissible value. Have I used that term before, non-permissible value? I mean, it's exactly like it might. The words might imply non-permissible. What's the value you can't use? In this example here, you can't use 2. Right. Now we should talk a bit about why you can't use 2. Are you not going to be allowed to use 2 because it's going to create a hole in the graph or an asymptote? Will these two functions here divide nicely? No. So if they don't divide nicely, it means it must have been an asymptote where x was 2. If they did divide nicely, I'm going to put a little circle on the graph implying that there's a hole there. But okay. Now, it probably has somewhat of a similar whoosh, whoosh kind of shape to it, but at this point here, I really can't know all of the details. So at this point here, on a graph like this, I'd expect you to graph it out, just so you guys know. The only one that you could really work with is like anything that kind of looks like a 1 over x graph. So 4x over 5 and x minus 2. Graph it out. And I mean, yeah, it did kind of have that whoosh, whoosh look to it, but it's kind of in a different spot now, hey? A couple of things have changed. I mean, yes, there is my asymptote still at 2. I predicted that. But check out, the graph over here is actually like above the axis. That's different. It wasn't above the axis last time. And then, it shoots straight down here, but then it kind of levels out here as well. But did it look at its core roughly like our reciprocal graph we were expecting? Yeah, it had that sort of property to it. Okay, let's talk domain and range. Just to shorten things up, I'll just talk about the numbers that it can't equal. What's the one number that x cannot equal? 2, right? Because you can't divide by the 2 on the bottom. But you know how on the previous graph, it looked like 0 is the line that it seems to like flatten out on both sides here? It's clearly not at 0 anymore, right? Like it's definitely gone over the axis. So one of the things we're going to have to try to figure out is what is happening right here. Where is that sort of leveling off? Okay. Now, the three of you who are taking calculus, this is where you find the limit as n approaches infinity. And if you know how to do that, you're welcome to. But this is just going to save you time. Here's what I recommend to you guys to do. Go to your second table set and make it so that your table's not starting at like something like -2. Make it go to like say 100. And then go to your table and see what y is getting close to. And I've got like 4 point something. Okay, well, maybe you don't believe it. Go back to your table set and make y go to maybe 1,000. Let's see what's happening way over here in the future when x is 1,000. Go back to your table, and yeah, it looks like it hasn't gotten below 4. Does that make sense? Right. That's how I'm going to expect you guys to more or less figure out the y asymptote. You just kind of like got to use your calculator to calculate it. Just so you're aware, this 4 right here is the rationale y. And I could show you calculus if you'd like, because I know you guys have kind of done this already. But if you don't care, then just literally just plug in, a really large x value and see what y starts to do. Just make sure you go large enough. Don't like make it go to, 7. Don't look at the table. That might not be enough to fully get a picture of it. So x can't be 2, and it looks like y could never be 4. Sound good? Moving forward. What about this one? I'm going to write it just slightly differently. I had to write it in this format here just based on how my computer works. But you guys could write it like this. 3 over x plus 3 minus 2. You could write it kind of like that. Or here's another way of writing it. You could write it as 3 times 1 over x plus 3 minus 2. Yeah, see how I'm kind of writing that there? This is one that I think we could do without a calculator. What does, what's the one value you can't use? -3. Does it look like that's going to create a hole in the graph or an asymptote? So far an asymptote. We actually haven't done a hole in the graph in a while, right? But if something factored and canceled, that might change it. But it looks like I should throw an asymptote line in here at -3. Now, at its core, though, doesn't this kind of look like a 1 over x graph? But I've done a few things to it. What would a 3 in front of that function do to it? This is 3 in front due to a graph. Yeah, it makes it taller, right? So you'd have your whoosh, whoosh graph that's now a taller whoosh graph. Right? This x plus 3 right here would slide the graph over 3 units. And what would the -2 do to the graph? Yeah, down 2. I'm actually going to start with the down 2 units because normally my asymptote would have been at 0. So if I slide it down 2 units, it looks like I should have an asymptote there. So it looks like I moved the graph over 3 to the left, down 2, and I just need to make the graph a little taller than normal. So you know how the graph usually is like right tight to the axis? Maybe I'll have it like it's going to get there, in its eventuality, right? I'm making it a little bit taller. Maybe I'll put it like there to there. Kind of see how like I've kind of made these like points maybe just a little bit higher than they normally would be? They're still going to eventually get lower and lower, but they're just taller. Yeah, Michael. This -2 though is not in the brackets here though. Right, like see the way I've notated this? It's 3 over x plus 3, stop. Then after that fraction, -2. Yeah, that's why I wanted to rewrite it like this right here, because the way I wrote it in text didn't quite illustrate what I was hoping for here. You get what I'm saying? So it's the -3 right there that's the problem. Good question though, right? Like that's a missing or improperly located bracket would change everything. So, okay, let's talk domain and range. I mean, let's just keep it to the simple version here. What's the one value x can't be? -3. What's the one value y can't be? -2, right? Because we took our original reciprocal graph and just slid it down 2, that's all. I mean, I know it looks like it's not getting close yet, but the only reason why I drew it that far out, does that make sense to you guys what I'm doing here? Is that it's 3 times taller, right? If the graph went 3 times over, it's eventually going to get down there. I just, I'm trying to show that it's taking its time. And if you wanted to, you could probably throw this in your graphing calculator, but I'm trying to encourage you when you can not to use it. Okay, let's try this one here. X squared minus 7x plus 10 over x squared minus 4. Right off the bat, you got a quadratic over a quadratic. Maybe the first thing we should do is start factoring. So make it like, say, x minus, what is it, x minus 5, x minus 2, and then x plus 2, x minus 2. You guys all capable of doing that factoring without any issues? Awesome. You know not to walk into the holes on Mario. Got that one down. Now we got to fight Bowser at the end of the game. Okay. What's up with the x minus 2s? Cancel. Okay, that's nice. What does that mean, though, if something cancels? There's going to be a hole in the graph. Now, I don't know where to put the hole, but somewhere on this line of x equals 2, I'm going to need a circle. So just temporarily, I'm going to draw this. Can you guys not draw this, though, because you can't do this later, but I'm temporarily going to draw a circle somewhere here, and later on, I'm going to select this circle, and I'm going to put it wherever it's supposed to go. Does that make sense? But don't you draw it yet, because you don't have that ability to. I don't think you have the ability to move something on your paper, right? Okay, now we also still have an asymptote, right? On the bottom of our fraction, we still have an x plus 2, which means that minus 2 is still a non-permissible value. So I'm going to draw in an asymptote at minus 2. Unfortunately, the rest of this graph doesn't really fit the same format of your regular reciprocal graph. So I don't know exactly what it's going to look like. I wouldn't expect, like there's some graphs where I'd expect you should be able to have a picture of it before you use your calculator. This one here, you're just going to want to graph it. So, but at least going into my graph, I know a couple of properties of it. So let's try graphing. Let's go bracket x squared minus 7x plus 10. And then we'll divide by new bracket again, x squared minus 4. Graph. Right. Again, it kind of has that whoosh, whoosh kind of shape to it, which makes sense. That's very, very, very consistent on rational graphs. So if I just kind of draw it in here, it didn't actually get very close to the axis right here, did it? I should explore that later. And then right here, and then does it look like it goes over the x-axis? It does. Like I should, go to my window, make my table go to like say 10. Oh, go to my table. Oh yeah, it's clearly over the axis at some point, right? So you know what I should do? I should find out how high it actually kind of levels off at, what its limit is, if you know that terminology. So maybe I'll go to my table set and I'll make x be like, I don't know, 10,000. And then go to my table and see, well, if it's at 10,000, it looks like y starts to level off at 0.99 repeating, which is essentially 1. So it looks to me like this guy levels off at 1, and it must level off at 1 on the other side here as well. You can confirm that, by the way, by doing like second table set and then make it like, say, negative 1,000, just to confirm that way over here when x is negative 1,000. Yeah, it looks like it's 1.0 something. It's getting close to 1. The logic makes sense. But now I need to do this part right here. I have to include my hole in the graph. Don't forget that. A lot of kids, when they work on a graph like this, and they love throwing this on a diploma because This is a logical place where a kid would forget something, right? They would look at this graph and they'd say x can't be negative 2. Got it. And what they've missed is that x also can't be positive 2. Makes sense. So when you're considering when you're considering what x can't be, don't forget to make x not be positive 2 and negative 2. There's 2 issues. Well, that means there's also 2 issues for y. We've already found one of the values that y can't be. What's one of the values y can't ever reach? 1. Because didn't we find that like this thing was leveling off at 1? It never quite got to the value of 1. Right? That's where like the horizontal asymptote was. So that's one of our issues. However, there's also one more issue. So 1, like plus 1 is a problem. But there's also a problem just slightly below it. Right there. Wherever our hole happens to be. I didn't draw my graph probably all that well. But you guys get what I'm saying here is that there's a problem with where the hole is. Because the hole causes an issue for the x value and for the y value. So we have to try to find where that hole happens to be. Now, what some kids will do is they'll go into their table and they'll make sure it starts back at a reasonable value. And they'll start looking through their table and they'll go, where's the error? And at 2, it looks like I found the error for x. That's fantastic. But it doesn't tell you what the y location would be there. Now, if I look at the numbers there, it's somewhere between, like, say, -1 and -0.4. So, like, I know about where it is, but about isn't going to cut it, right? So, any thoughts about how to find exactly where this hole is going to be? And plug it into the canceled out function. Right? You know how we had a function up here of x minus 5, x minus 2, x plus 2, x minus 2, and we canceled away an issue? Well, now rewrite it as 2 minus 5 over 2 plus 2. Right? That would be the remaining part of the function. Right? Now, I couldn't plug 2 in right here, because that causes a problem, but what's the hold up here? There's nothing stopping me now. 2 minus 5 gives you -3. 2 plus 2 gives you 4. Now I know where that hole for y happens to be. The hole for y is at -3 over 4. You probably won't find that with your calculator. There is a way that you could use your calculator, but it's even slower. You could then graph the canceled function, like the x minus 5 and the I should better divide them. And the come on, Chris, you can do this. X plus 2. I could graph the other function, and if I graphed the second function on top of it, you shouldn't see anything different. Right? Like I have 2 functions currently being graphed, and I literally see no differences. And if I went to my table of values, the table of values should line up perfectly with one exception. On the first graph, there's an error at 2. On the second graph, it tells you where the point would have been. And look, it's at, you guys see that from where you're at? I can. It's -0.75, -3 over 4. That makes sense? Okay, let's fast forward here. What else do I have in this set of notes? Okay, just a summary slide it looks like here. So to make sure we're clear, asymptotes are what happens when the graph does not divide and something's left in the denominator. A point of discontinuity, called a hole in the graph, is where a graph does divide and it causes a hole. Most common mistake kids make is when they talk about the range, they forget that there's a hole for the y value along with the x value. Right? Your domain on this one is everything but 2. Your range is not everything. Your range is everything but -1. Don't forget the hole as well. Why don't we leave this one here? I'm sure you guys can handle that. Take a look at this one real quick. I want to show you that when it comes to these graphs here, just a subtle difference can make all the change in the world. This is x squared minus 2x over 4 minus 2x. And this is x squared plus 2x over 4 minus 2x. Can you guys see how the only difference between these graphs is a negative sign? That is the only difference. And it drastically changed the graph. Let's talk about why. If I were to factor this guy, I could factor it to x, bracket x minus 2. And on the bottom, I could factor out, say, a -2. And it would also leave you with x minus 2. You have to be a little creative on the bottom. You have to factor a negative out, even though the first term is positive. But hopefully you guys can visually see that I can find a way to cancel something. Therefore, if it can cancel, that explains the hole in the graph. However, it's almost the exact same function, except now it's x bracket x plus 2 over minus 2 bracket x minus 2. Now do these things cancel? Nope. Therefore, what was a hole in the graph over here on this one has turned into an asymptote instead. So I can't tell you what the graph is going to look like for sure. You're probably going to have to graph some of these on your calculator. That is a reasonable expectation. But you should be able to tell me a couple of properties without looking at the graph. Like you should be able to tell me whether it's a hole or whether it's an asymptote. Like you should know that much at least, right? The rest of the shape is still a little up for grabs. Like whether it has like this sort of look to it or whether it does like the whoosh, whoosh kind of thing to it. Yeah. Okay. Okay, let's do this last one here, and then I don't know that I'm going to get to part 2 today, really. Should I just call her quits here? Or should I try to go on to the next one? It's not really going to happen, is it? Okay, yeah, I'll just give you 10 minutes to work on stuff. Let's do this last one, though, because this is something that is like one of those kind of challenge questions you might see written as like a numeric response thing. I've seen this one before, written as maybe like, say, ax minus b over 1x squared plus cx plus d. And like their goal is for you to eventually write an equation of a function. And when you're done, you're going to tell me what the a, b, c, and d values are. That makes sense? So, okay, let's try this. It tells you there's a rational function. Okay, well, right off the bat, even just that first 3 words tells me something. Tells me I can write my function as something with a fraction in it. That's not unuseful. Not unuseful. It's slightly helpful. It tells you have a linear function on the top. Okay. Hence the reason why I kind of wrote it as like a x minus b sort of thing, or like I wrote it in that sort of format. And then it said there's a quadratic function on the bottom. Well, you know what? Quadratic function can sometimes be written in like a sort of a factored form. So maybe what I'll do before I get too far is rather than trying to write in stuff that I don't know about yet, I'll just leave it as like some brackets. If you kind of get what I'm saying here. Here's a linear on the top. I mean, I'll fill in the numbers later once I know more about it, but this is a linear on the top, and then the quadratic on the bottom would have 2 factors to it. That seems logical, right? And then I read, it says it has an asymptote where x equals 3. What does that help clue me into? On the bottom. Right? Should be an x minus 3 on the bottom. Right? A non-cancelable, that's a word, a non-cancelable x minus 3 on the bottom. It means that I know that this top guy right here is not x minus 3. Because if it was, it would have canceled. Keep reading. Then it gives you a point of discontinuity at 1, negative 4. The 1 is the more important number because it means that you have a hole in the graph when x is 1. That actually tells you what the top and the bottom of the equations happen to be. Right? There must be an x minus 1 on the top and on the bottom. Hey, not bad. I seem to have the core of an equation put together. This x minus 3 provides the asymptote. These x minus 1s right here provide the hole in the graph. Let's graph it. So that's our answer. So, now, if I graphed it, it would give me x minus 1, close brackets, divided by like a big open bracket, then another one for, say, the x minus 3. Close the bracket for the x minus 3, open a bracket for the x minus 1, close the bracket for the x minus 1, and then close the extra bracket for the denominator. And if I graph it, it should look kind of like what we've been talking about for the last little while. Now, I'm fairly certain by looking at my table of values that I have an error at 1. That's good. And I have an asymptote at 3. The big issue, though, is my hole in the graph actually at minus 4? Here's one way I could figure that out. I could put a second line on here at -4. I'm going to put a second line on here at -4, right across there. Now, if there truly is a hole in the graph, and I go and I do intersect, you guys recall how to do intersect? If there truly is a hole in the graph, what would your calculator say if you tried to intersect? It would say some sort of error code at you, because it would be like, it's asking you where they cross, and your calculator would spit back, but it doesn't cross, right? So if I try to do the whole first curve, second curve, guess sort of thing here, oh look, it did intersect. What does that mean? It means the hole's in the wrong spot, because there's supposed to be a hole at 1, -4, but clearly I should have had a hole there, right? It shouldn't have been able to cross at 1, -4 if there truly was a hole on the -4 line. You got what I'm saying there? So just like with every other function that I've been teaching you guys about since we learned this before, there is a leading coefficient that you need to solve for, just like every other one you've been doing, which some kids find frustrating because they're like, okay, fine, stupid leading coefficient, been here, done that. But then they're like, but at what point am I going to plug in? 1 and 4, except for one problem here. You can't plug in 1 right here and right here. So you have to like temporarily use the version that has the these guys canceled and just do the x minus 3 version, because then you can plug in -4 for y and 1 for x. You can't do it in the version that has the x minus 1s in it, that's all. So -1 is your y value, 1 is your x value. So -4 equals a over -2. So there is a leading coefficient of 8. Follow that? Stupid leading coefficients. Every graph, right? Okay, here's what it means then. I'm going to go back up to this top one that I had been writing earlier here. And now I can fill it in as 8, x minus 1, x minus 3, x minus 1. So if I wanted to then write it in the format that the diploma asked you for, I would expand it and you would get 8x minus 8 over x squared minus 4x plus 3, and then your answer would have been like, say, 8, 8, 4, 3. That's hard, eh? Like, you really got to know what you're doing on that one. But hopefully now that I've shown you an example like this, it'll give you a fighting chance in case you get one where you have to like write yourself your own function. Just before we take off here, let's re-talk through then the main concepts I used. First concept is it said there was going to be a linear over a quadratic, so I drew a couple of brackets in those locations. The asymptote led me to writing the x minus 3 down here. The hole in the graph with an x value of 1 led me to write this one and this one. I did a quick test just to prove to you guys that it actually wasn't done, because you guys should know by now. You will know. You need a leading coefficient. So, I mean, 1 and -4 is the point I can try to plug in. It's just I can't plug it in when I currently have this function here with the 2x minus 1s. So I just used the function that had the x minus 1s canceled. That solved my problem. Right. Plugged in the 1 and the -4. Got myself my leading coefficient value. Plugged it back in up here. And I distributed it to get like the numbers that would go here and there.
In our gym. Reminder that it is Crazy Hair Day on Friday, and that there's green cupcakes being sold for it. I don't know how much. But that one's still on Friday.
Big money. Okay. I think I've talked to you guys about my 3 levels of understanding. Level 1, I should call it level 0 actually. Over your head. Anybody at the over their head stage are willing to tell me that? Okay, mid-level. Could you follow it? Like you watched me do all those steps and you're like, yes, I understand 1 to 2 to 3 to 4. Anybody feel like they're at stage 3 where they might be able to do it themselves? Okay. Write your own equation then. right? Like, now that I've given you something like this, I mean, kind of make up your own equation. Just make up some new values here. Make it a linear function over a quadratic again. Just change your asymptote to x equals 2, right? And then make your point of discontinuity be 3, 7. Right? You may end up getting a fraction along the way, but like you could make your own question up. Make sense? Okay, I'll stop here for now. You guys can see why I did split these into 2 halves, because it was ambitious to do both halves. We'll do part 2 tomorrow. Part 2 tomorrow, by the way, just to give you a heads up, is all about the third half of my 3 outcomes. Outcome 1, the subtle nuances of it. Outcome 2, the graphs. Outcome 3 is solving. This is going to be a review of what you guys learned last year in 20-1, where you now have to be able to solve these guys. So most of my equations here should all be about how to solve for what x is equal to. Do you guys recall doing this at all last year? I used my Johnny Depp analogy, wait for the opportune moment on these as well. The opportune moment is when to cross multiply. So anyways, that's part 3. And then we'll write a quiz after that. So okay, I guess you have like 3 minutes. So okay.